In this lecture, we will discuss the processes that shape Earth, including the rocks and minerals contained within it. We will also take a more in-depth look at climate change and ecosystems. Let's get started. The third planet from the Sun, Earth has countless properties that make it unique from the other planets and planetary bodies within the solar system and within the Milky Way galaxy. It is one of four rocky planets, along with Venus, Mercury, and Mars, and is the fifth largest planet behind Neptune, Uranus, Saturn, and the largest, Jupiter. Earth is the densest major body in the solar system at 5.52 grams per cubic inch. It is composed of 34.6% iron, 29.5% oxygen, 15.2% silicon, 12.7% magnesium, 2.4% nickel, 1.4% sulfur, and 0.05% titanium. Earth is positioned within the habitable zone of the solar system at around 92 million miles from the Sun, making Earth unique within the solar system. This zone is defined as the distance from the Sun where water can be found in solid and liquid form. If Earth were in Mercury or Venus position, its atmosphere and water would evaporate. If Earth were pushed out to the position of Mars or further out near the gas giants, it would be too cold to sustain liquid water or life. Around the equator, Earth is 7,926 miles in diameter and 24,902 miles in circumference. From pole to pole or along the meridional axis, Earth is slightly smaller at 7,899 miles with a 24,860 mile circumference. This is due to the Earth's rotation, which causes Earth to bulge at the equator and flatten at the poles, creating a shape called an oblate spheroid. Earth's surface is covered with 71% water. This liquid water is essential for life and is also responsible for the erosion experienced on Earth's land masses. The effects of erosion and tectonic plate movement have rendered Earth's surface younger than the actual age of the planet by about 500 million years. In other words, the Earth is believed to be 4.5 to 4.6 billion years old. However, the oldest known rocks are 4 billion years old, with rocks older than 3 billion years old being rare. The lithosphere is the solid outer part of Earth. The lithosphere includes the brittle upper portion of the mantle and the crust, the outermost layer of Earth's structure. It is bounded by the atmosphere above and the asthenosphere below. There are two types of lithosphere, oceanic lithosphere and continental lithosphere. Oceanic lithosphere is associated with oceanic crust and is slightly denser than continental lithosphere. The mantle contains the bulk of Earth's interior. The mantle lies between Earth's dense superheated core and its thin outer layer, the crust. The mantle is about 1,802 miles thick and makes up a whopping 84% of Earth's total volume. The rocks that make up Earth's mantle are mostly silicates, a wide variety of compounds that share silicon and oxygen structure. Common silicates found in the mantle include olivine, garnet, and pyroxene. Other major types of rocks found in the mantle include magnesium oxide. Other elements found in the mantle include iron, aluminum, calcium, sodium, and potassium. The temperature of the mantle varies greatly from 1,832 degrees Fahrenheit near its boundary with the crust to 6,692 degrees Fahrenheit near its boundary with the core. The outer core is about 1,367 miles thick and is mostly comprised of liquid iron and nickel. The nickel-iron alloy of the outer core is very hot, between 1,832 and 9,932 degrees Fahrenheit. The liquid metal of the outer core has very low viscosity, meaning it is easily deformed and malleable. It is the site of violent convection. The churning metal of the outer core creates and sustains Earth's magnetic field. The inner core is a hot, dense ball of mostly iron. It has a radius of about 758 miles thick. Temperature in the inner core is about 9,392 degrees Fahrenheit. The temperature of the inner core is far above the melting point of iron. However, unlike the outer core, the inner core is not a liquid or even molten. The inner core's intense pressure, the entire rest of the planet and its atmosphere, prevents the iron from melting. Everything in Earth's system can be placed into one of four major subsystems: land, water, living things, or air. These four subsystems are called spheres. Specifically, they are the lithosphere for the land, hydrosphere for the water, biosphere for living things, and atmosphere for the air. Each of these four spheres can be further divided into subspheres. The lithosphere contains all of the cold, hard, solid land of the planet's crust or surface, the semi-solid land underneath the crust, and the liquid near the center of the planet. The surface of the lithosphere is very uneven. There are high mountain ranges like the Rockies and Andes, huge plains or flat areas like those in Texas, Iowa, and Brazil, and deep valleys along the ocean floor. The solid, semi-solid, and liquid land of the lithosphere form layers that are physically and chemically different. If someone were to cut through the Earth to its center, these layers would be revealed like layers of an onion. The outermost layer of the lithosphere consists of loose, rich soil nutrients, oxygen, and silicon. Beneath that layer lies a very thin, solid crust of oxygen and silicon. Next is a thick, semi-solid mantle of oxygen, silicon, iron, and magnesium. Below that is a liquid outer core of nickel and iron, and at the center of Earth is a solid inner core of nickel and iron. The hydrosphere contains all of the solid, liquid, and gaseous water of the planet. It ranges from 10 to 20 kilometers in thickness. The hydrosphere extends from Earth's surface downward several kilometers into the lithosphere and upward about 12 kilometers into the atmosphere. A small portion of the water in the hydrosphere is fresh or non-salty. This water flows as precipitation from the atmosphere down to Earth's surface as rivers and streams along Earth's surface and groundwater beneath Earth's surface. Most of Earth's fresh water, however, is frozen. 97% of Earth's water is salty. The salty water collects in deep valleys along Earth's surface. These large collections of salty water are referred to as oceans. Water near the poles is very cold, while water near the equator is very warm. The differences in temperature cause water to change physical states. Extremely low temperatures like those found at the poles cause water to freeze into a solid such as polar ice cap, a glacier, or an iceberg. Extremely high temperatures like those found at the equator cause water to evaporate into a gas, which eventually comes back as rain. The biosphere contains all of the planet's living things. This sphere includes all of the microorganisms, plants, and animals of Earth. Within the biosphere, living things form ecological communities based on the physical surroundings of an area. These communities are often referred to as biomes. Deserts, grasslands, and tropical rainforests are three of the many types of biomes that exist within the biosphere. The atmosphere contains all of the air in Earth's system. It extends from less than 1 meter below the planet's surface to more than 10,000 kilometers above the planet's surface. The upper portion of the atmosphere protects the organisms of the biosphere from the sun's ultraviolet radiation. It also absorbs and emits heat. When air temperature in the lower portion of the sphere changes, weather occurs. As air in lower atmosphere is heated or cooled, it moves around the planet. This result can be as simple as a breeze or as complex as a tornado. There are three main rock types found in Earth's crust: igneous, sedimentary, and metamorphic. Let's briefly take a look at each one of these as they play an important role in sustainability because we as humans all live on the surface of the Earth. Igneous rocks, from the Latin word for fire, form when hot, molten rock crystallizes and solidifies. The melt originates deep within the Earth near active plate boundaries or hotspots, then rises towards the surface. Igneous rocks are divided into two groups: intrusive or extrusive, depending on where the molten rock solidifies. Intrusive or plutonic igneous rocks form when magma is trapped deep inside the Earth. Great globs of molten rock rise towards the surface. Some of the magma may feed volcanoes on Earth's surface, but most remains trapped below, where it cools very slowly over many thousands or millions of years until it solidifies. Slow cooling means the individual mineral grains have a long time to grow, so they grow to a relatively large size. Intrusive rocks have a coarse grained texture. Extrusive or volcanic igneous rock is produced when magma exits and cools above or very near the Earth's surface. These are the rocks that form at erupting volcanoes and oozing fissures. The magma, called lava when molten rock erupts on the surface, cools and solidifies almost instantly when it's exposed to the relatively cool temperatures in the atmosphere. Quick cooling means that mineral crystals don't have much time to grow, so these rocks have a very fine-grained or even glassy texture. Hot gas bubbles are often trapped in the quenched lava, forming a bubbly vesicular texture. Here we see some example of igneous rocks. Granite, coarse or medium-grained extrusive igneous rock that is rich in quartz and feldspar. It is the most common plutonic rock of the Earth's crust, formed by the cooling of magma at depth. Diorite is an intrusive igneous rock formed by the slow cooling underground of magma that has a moderate content of silica and a relatively low content of all alkali metals. Basalt is a dark-colored, fine-grained igneous rock composed mainly of plagioclase and pyroxene minerals. It most commonly forms as an extrusive rock, such as a lava flow, but can also form in small intrusive bodies, such as an igneous dike or thin sill. It has a composition similar to gabbro. The difference between basalt and gabbro is that basalt is a fine-grained rock, while gabbro is a coarse-grained rock. Obsidian is an igneous rock that forms when molten rock material cools so rapidly that atoms are unable to arrange themselves into a crystalline structure. It is also known as volcanic glass and can be used to create very sharp objects such as arrowheads and knives. Gabbro is a coarse-grained igneous rock that is relatively low in silica and rich in iron, magnesium, and calcium. Such a rock is described as mafic. Gabbro is composed of pyroxene and calcium-rich plagioclase with minor amounts of hornblende, olivine, and accessory minerals. Peridotite is a generic name used for coarse-grained, dark-colored, ultramafic igneous rocks. Peridotites usually contain olivine as their primary mineral, frequently with other mafic minerals such as pyroxenes and amphiboles. They are formed deep in the earth and sometimes can contain diamonds in a variety called kimberlite. Andesite is the name of a family of fine-grained extrusive igneous rocks that are usually light to dark gray in color. They have a mineral composition that is intermediate between granite and basalt. Andesite is a rock typically found in volcanoes above convergent plate boundaries between continental and oceanic plates. Pumice is a light-colored, extremely porous igneous rock that forms during explosive volcanic eruptions. It is used as aggregate in lightweight concrete, as a landscaping aggregate, and as an abrasive in a variety of industrial and consumer products. Many specimens have a high enough porosity that they can float on water until they slowly become waterlogged. Sedimentary rocks are formed from pre-existing rocks or pieces of once living organisms. They form from deposits that accumulate on Earth's surface. Sedimentary rocks often have distinctive layering or bedding. Clastic sedimentary rocks are a group of rocks most people think of when they think of sedimentary rocks. Clastic sedimentary rocks are made up of pieces of pre-existing rocks. Pieces of rock that are loosened by weathering, then transported to some basin or depression where the sediment is trapped. If the sediment is buried deeply, it becomes compacted and cemented, forming sedimentary rock. Biologic sedimentary rocks form when large numbers of living things die. Chert is an example of this type of rock, and this is one of the many ways limestone can form. Limestone can also form by precipitating directly out of the water. Here are some examples of sedimentary rocks. Conglomerate is a clastic sedimentary rock made up of rounded clasts that are greater than 2 millimeters in diameter. The spaces between the clasts are generally filled with sand and clay-sized particles. The rock is bound together by a cement that is usually composed of calcite or quartz. Breccia is a term most often used for classic sedimentary rocks that are composed of large angular fragments over 2 millimeters in diameter. The spaces between the large angular fragments are filled with a matrix of smaller particles and a mineral cement that binds the rock together. Sandstone is a sedimentary rock composed of sand grains size minerals, rock, or organic material. It also contains a cementing material that binds the sand grains together and may contain a matrix of silt or clay-sized particles that occupy the spaces between the sand grains. Sandstone is one of the most common types of sedimentary rock and is found in sedimentary basins throughout the world. Siltstone is a sedimentary rock composed mainly of silt-sized particles, which are slightly smaller than sand-sized particles. It forms where water, wind, or ice deposits silt, and then the silt is compacted and cemented into a rock. Silt accumulates in sedimentary basins throughout the world. It represents a level of current, wave, or wind energy between where sand and mud accumulate. Shale is a fine-grained sedimentary rock that forms from the compaction of silt and clay-sized mineral particles that we commonly call mud. This composition places shale in a category of sedimentary rocks known as mudstones. Shale is distinguished from other mudstones because it is fissile, which means laminated. Laminated means that the rock is made up of many thin layers. Fissile means that the rock readily splits it into thin pieces along those thin layers. Coquina is a sedimentary rock composed entirely of sand-sized fossil debris. The fossils are usually mollusk or gastropod shells and shell fragments. Brachiopod, trilobite, coral, ostracod, and other invertebrate shell debris is present in many coquinas as well. The fossil debris of coquina is composed of calcium carbonate, making coquina a variety of limestone. Metamorphic rocks start out as some other type of rock, but have been substantially changed from their original igneous, sedimentary, or earlier metamorphic form. Metamorphic rocks form when rocks are subjected to high heat, high pressure, hot mineral-rich fluids, or more commonly, some combination of these factors. Conditions like these are found deep within the earth or where tectonic plates meet. The process of metamorphism does not melt the rocks, but instead transforms them into denser, more compact rocks. New minerals are created either by rearrangement of mineral components or by reactions with fluids that enter the rocks. Pressure or temperature can even change previously metamorphosed rocks into new types. Metamorphic rocks are often squished, smeared out, and folded. Despite these uncomfortable conditions, metamorphic rocks do not get hot enough to melt, or they would become igneous rocks. Here are some examples of metamorphic rocks. There are two main types of metamorphic rocks, foliated and non-foliated. Foliated means the parallel arrangement of certain mineral grains that gives the rock a striped appearance. Foliation forms when the pressure squeezes or flattens or elongates minerals within a rock so they become aligned. These rocks develop a platy or sheet-like structure that reflects the direction that the pressure was applied. Non-foliated metamorphic rocks do not have a platy or sheet-like structure. Slate is a fine-grained, foliated metamorphic rock that is created by the alteration of shale or mudstone by low-grade regional metamorphism. It is popular for a wide variety of uses such as roofing, flooring, and flagging because of its durability and attractive appearance. Phyllite is a foliated metamorphic rock that has been subjected to low levels of heat, pressure, and chemical activity. It is composed mainly of flake-shaped mica minerals in parallel alignment. The strong parallel alignment of the mica grains allows the rock to be easily split into sheets or slabs. The alignment of the mica grains gives phyllite a reflective sheen that distinguishes it from slate, its metamorphic precursor or protolith. Phyllite is usually gray, black, or greenish in color and often weathers to a tan or brown. Its reflective sheen often gives it a silvery, non-metallic appearance. Quartzite is a non-foliated metamorphic rock composed almost entirely of quartz. It forms when a quartz-rich sandstone is altered by the heat, pressure, and chemical activity of metamorphism. Metamorphism recrystallizes the sand grains and the silica cements that binds them together. The result is a network of interlocking quartz grains of incredible strength. Schist is a foliated metamorphic rock made up of plate-shaped mineral grains that are large enough to see with an unaided eye. It usually forms on a continental side of a convergent plate boundary where sedimentary rocks such as shales and mudstones have been subjected to compressive forces, heat, and chemical activity. This metamorphic environment is intense enough to divert the clay minerals of the sedimentary rocks into platy metamorphic minerals such as muscovite, biotite, and chlorite. To become schist, a shale must be metamorphosed in steps through slate and then through phyllite. If schist is metamorphosed further, it might become a granular rock known as gneiss. Gneiss is a foliated metamorphic rock identified by its bands and lenses of varying mineral composition. Some of these bands or lenses contain granular minerals that are bound together in an interlocking texture. Other bands contain platy or elongated minerals that show a preferred orientation that parallels the overall banding in the rock. It is this banding appearance and texture, rather than composition, that defines a gneiss. Finally, marble is a metamorphic rock that forms when limestone is subjected to the heat and pressure of metamorphism. It is composed primarily of the mineral calcite, which usually contains other minerals such as clay minerals, micas, quartz, pyrite, iron oxides, and graphite. Under the conditions of metamorphism, the calcite in the limestone recrystallizes to form a rock that is a mass of interlocking calcite crystals. A related rock, dolomitic marble is produced when dolostone is subjected to heat and pressure. In describing the rock cycle, we can start anywhere we like, although it's convenient to start with magma. Magma can either cool slowly within the crust, forming intrusive igneous rock, or erupt onto the surface and cool quickly, forming extrusive igneous rock. Intrusive igneous rocks typically crystallize at depths of hundreds of meters to tens of kilometers below the surface. To change its position in the rock cycle, intrusive igneous rock has to be uplifted and exposed by the erosion of overlying rocks. Through the various plate tectonics related processes of mountain building, all types of rocks are uplifted and exposed at the surface. Once exposed, they are weathered both physically by mechanically breaking down of the rock and chemically by weathering of the minerals, and weathering products, mostly small rock and mineral fragments, are eroded, transported, then deposited as sediments. Transportation and deposition occur through the actions of glaciers, streams, waves, wind, and other agents, and sediments are deposited in rivers, lakes, deserts, and the ocean. Unless if they are re-eroded and moved along, sediments will eventually be buried by more sediments. At depths of hundreds of meters or more, they become compressed and cemented into sedimentary rock. Again, all through various means, largely resulting from plate tectonic forces, different kinds of rocks are either uplifted to be re-eroded or buried deeper within the crust where they are heated up, squeezed, and changed into a metamorphic rock. The entire cycle can then repeat itself once again. Water is essential to life on Earth. In its three phases, solid, liquid, and gas, water ties together the major parts of the Earth's climate system: air, clouds, the oceans, lakes, vegetation, snowpack, and glaciers. The water cycle shows the continuous movement of water within the Earth and atmosphere. It is a complex system that includes many different processes. Liquid water evaporates into water vapor, condenses to form clouds, and precipitates back to Earth in the form of rain or snow. Water in different phases move through the atmosphere, transportation. Liquid water flows across the land as runoff, into the ground, which is infiltration and percolation, and through the ground, which is groundwater. Groundwater moves into plants and evaporates from plants into the atmosphere, which is known as transpiration. Solid ice and snow can turn directly into gas, known as sublimation. The opposite can also take place when water vapor becomes a solid, known as deposition. The carbon cycle is the process that moves carbon between plants, animals, and microbes, minerals in the earth, and the atmosphere. Because only a tiny number of atoms reach the Earth from space, our planet is called a closed system. This means the Earth does not gain or lose carbon, but carbon does move constantly. Most carbon on Earth is stored in rocks and sediments. The rest is in the ocean, atmosphere, and in living organisms. Scientists use the term carbon sinks to refer to places where carbon is stored away from the atmosphere. Plants constantly exchange carbon within the atmosphere. Plants absorb carbon dioxide during photosynthesis, and much of this carbon dioxide is then stored in roots, permafrost, grasslands, and forests. Plants and the soil then release carbon dioxide when they decay. Other organisms also release carbon dioxide as they live and die. For examples, animals exhale carbon dioxide when they breathe and release carbon dioxide when they decompose. The ocean also exchanges carbon with the atmosphere by absorbing carbon, which then sinks as it cools. In addition, carbon is stored in rocks and other geologic deposits. For example, coal and other fossil fuels are made of carbon from plants that has been stored under the Earth's surface for millions of years. Humans have a huge effect on the carbon cycle when we burn wood, fossil fuels, and other forms of carbon. This action releases the stored carbon in the atmosphere, where it becomes a greenhouse gas. Greenhouse gases are gases in the atmosphere that absorb and release heat. Carbon monoxide is a colorless, odorless gas that can be harmful when inhaled in large amounts. Carbon monoxide is released when something is burned. The greatest sources of carbon monoxide to outdoor air are cars, trucks, and other vehicles or machinery that burn fossil fuels. A variety of items in your home, such as unvented kerosene and gas space heaters, leaking chimneys and furnaces, and gas stoves, also release carbon monoxide and can affect air quality indoors. Breathing air with high concentration of carbon monoxide reduces the amount of oxygen that can be transported in the bloodstream to critical organs like the heart and brain. At very high levels, which are possible indoors or other enclosed environments, carbon monoxide can cause dizziness, confusion, unconsciousness, and even death. Very high levels of carbon monoxide are not likely to occur outdoors. However, when carbon monoxide levels are elevated outdoors, they can be of particular concern for those people with some type of heart disease. These people already have a reduced ability for getting oxygenated blood to their hearts in situations where the heart needs more oxygen than usual. They are especially vulnerable to the effects of carbon monoxide when exercising or under increased stress. In these situations, short-term exposure to elevated carbon monoxide may result in reduced oxygen to the heart accompanied by chest pain, also known as angina. In this section, we will dive deeper into what is climate change, what is causing it, and its effects. There is a slight review from the previous chapter in the beginning, however. Weather is the mix of events that happen each day in our atmosphere. Even though there's only one atmosphere on Earth, the weather isn't the same all around the world. Weather is different in different parts of the world and changes over minutes, hours, days, and weeks. Whereas weather refers to short-term changes in the atmosphere, climate describes what the weather is like over a long period of time in a specific area. Different regions can have different climates. To describe the climate of place, we might say what the temperatures are like during different seasons, how windy it usually is, or how much rain or snow typically falls. When scientists talk about climate, they are often looking at averages of precipitation, temperature, humidity, sunshine, wind, and other measures of weather that occur over a long period in a particular place. In some instances, they might look at these averages over 30 years. The modern record of atmospheric carbon dioxide levels began with observations recorded at Mauna Loa Observatory in Hawaii. This graph shows the station's monthly average carbon dioxide measurements since 1958 in parts per million. The seasonal cycle of highs and lows, small peaks and valleys, is driven by northern hemisphere summer vegetation growth, which reduces atmospheric carbon dioxide, and winter decay, which increases it. The long-term trend of rising carbon dioxide levels is driven by human activities. At Mauna Loa, the highest monthly value each year occurs in May. In May of 2023, carbon dioxide hit 424 parts per million, a new record. Carbon dioxide concentrations are rising mostly because of the fossil fuels that people are burning for energy. Fossil fuels like coal and oil contain carbon that plants pulled out of the atmosphere through photosynthesis over many millions of years. We are returning that carbon to the atmosphere in just a few hundred. Since the middle of the 20th century, annual emissions from burning fossil fuels have increased every decade, from close to 11 billion tons of carbon dioxide per year in the 1960s to an estimated 36.6 billion tons in 2022, according to the Global Carbon Budget of 2022. The greenhouse effect is a process that occurs when gases in Earth's atmosphere traps the sun's heat. This process makes Earth much warmer than it would be without an atmosphere. The greenhouse effect is one of the things that makes Earth a comfortable place to live. Sunlight, with the natural greenhouse effect process, makes Earth habitable. While around 30% of the solar energy, the light and the heat from the sun, that reaches our world is reflected back into space, the rest is either absorbed by the atmosphere or Earth's surface. This process, which is constantly happening around the globe, warms the planet. This heat is then radiated back up in the form of invisible infrared radiation. While some of this infrared light continues on into space, the vast majority gets absorbed by atmospheric gases, known as greenhouse gases, causing further warming. But higher concentrations of greenhouse gases, and carbon dioxide in particular, are causing extra heat to be trapped and average global temperatures to rise. For most of the past 800,000 years, much longer than human civilization has existed, the concentration of carbon dioxide in our atmosphere was roughly between 200 and 280 parts per million. But in the past century, that concentration has jumped. In 2013, driven up largely by the burning of fossil fuels and deforestation, carbon dioxide in Earth's atmosphere surpassed 400 parts per million, a concentration not seen on the planet for millions of years. As of 2023, it has reached more than 420 parts per million, which is 50% higher than pre-industrial levels. Carbon dioxide accounts for almost 80% of global human-caused emissions, and carbon dioxide sticks around for quite a while. Once it is emitted into the atmosphere, 40% still remains after 100 years, 20% after 1,000 years, and 10% as long as 10,000 years later. Some carbon dioxide is absorbed quickly, but some will remain in the atmosphere for thousands of years. Methane persists in the atmosphere for around 12 years, which is less time than carbon dioxide, but it is much more potent in terms of the greenhouse effect. In fact, pound for pound, its global warming impact is almost 30 times greater than that of carbon dioxide over a 100-year period. In the United States, methane accounted for more than 12% of human-generated greenhouse gas emissions in 2021. While methane can come from natural sources like wetlands, more than half of all global methane emissions come from human activities like natural gas production and livestock-based agriculture. Nitrous oxide is a powerful greenhouse gas. It has a global warming potential around 270 times that of carbon dioxide on a 100-year timescale and remains in the atmosphere on average a little more than a century. It accounts for about 6% of human-caused greenhouse gas emissions in the United States from sources like fertilizers and agriculture. Emitted from a variety of manufacturing industrial processes, fluorinated gases are man-made. There are four main categories: hydrofluorocarbons, perfluorocarbons, sulfur hexafluoride, and nitrogen trifluoride. Although fluorinated gases are emitted in smaller quantities than other greenhouse gases, they trap substantially more heat. Indeed, the global warming potential for these gases can be in the thousands to tens of thousands, and they have long-term atmospheric lifetimes, in some cases lasting tens of thousands of years. The most abundant greenhouse gas overall, water vapor, differs from the other greenhouse gases in that it changes in its atmospheric concentrations are linked not to human activities directly, but rather to warming that results from the other greenhouse gases we emit. Warmer air holds more water, and since water vapor is a greenhouse gas, the more water absorbs more heat, inducing even greater warming and perpetuating a positive feedback loop. The sulfur cycle describes the movement of sulfur through the atmosphere, mineral forms, and through living things. Although sulfur is primarily found in sedimentary rocks or seawater, it is particularly important to living things because it is a component of many proteins. The process of sulfur cycle is explained in the following. The sulfur is released by the weathering of rocks. The sulfur comes in contact with air and is converted into sulfates. Sulfates are taken up by plants and microbes and are converted into organic forms. The organic form of sulfur is then consumed by animals through their food, and thus sulfur moves into the food chain. When the animals die, some of the sulfur is released by decomposition while some enters the tissue of the microbes. There are several natural sources such as volcanic eruptions, evaporation of water, and breakdown of organic matter in swamps that release sulfur directly into the atmosphere. This sulfur falls on Earth with rainfall. Sulfur dioxide is a gaseous air pollutant composed of sulfur and oxygen. The largest source of sulfur dioxide in the atmosphere is the burning of fossil fuels by power plants and other industrial facilities. Smaller sources of sulfur dioxide emissions include industrial processes such as extracting metal from ore, natural processes such as volcanoes, and locomotives, ships, and other vehicles and heavy equipment that burn fuel with high sulfur content, such as diesel. Short-term exposures to sulfur dioxide can harm the human respiratory system and make breathing difficult. People with asthma, particularly children, are sensitive to these effects of sulfur dioxide. Sulfur dioxide emissions that lead to high concentrations of sulfur dioxide in the air generally also lead to the formation of other sulfur oxides known as SOXs. SOXs can react with other compounds in the atmosphere to form small particles. These particles contribute to the particulate matter pollution. Small particles may penetrate deeply into the lungs and in sufficient quantity can contribute to health problems. The phosphorus cycle is a very slow process. Various weather processes help to wash the phosphorus present in the rocks into the soil. Phosphorus is absorbed by the organic matter in the soil, which is used for various biological processes. Since phosphorus and phosphorus-containing compounds are present only on land, atmosphere plays no significant role in the phosphorus cycle. Phosphorus is found in the rocks in abundance. That is why the phosphorus cycle starts in the Earth's crust. The phosphate salts are broken down from the rocks. These salts are washed away into the ground where they mix with the soil. The phosphate salts dissolve in water are absorbed by the plants. However, the amount of phosphorus present in the soil is very less. That is why the farmers apply phosphate fertilizers on agricultural land. The aquatic plants absorb inorganic phosphorus from lower layers of water bodies. Since phosphate salts do not dissolve in water properly, they affect plant growth in aquatic ecosystems. The animals absorb phosphorus from the plants or by consuming plant-eating animals. The rate of the phosphorus cycle is faster in plants and animals when compared to rocks. When the plants and animals die, they are decomposed by microorganisms. During this process, the organic form of phosphorus is converted into the inorganic form, which is recycled to soil and water. Soil and water will end up in sediment and rocks, which will again release phosphorus by weathering. Thus, the phosphorus cycle starts over. The phosphorus fertilizers increase the level of phosphorus in the soil. Overuse of these fertilizers reduces the fertility of the soil and is also harmful to the microorganisms present in the soil. When these are washed away into the nearby water bodies, they are hazardous to aquatic life. The nitrogen cycle is a biogeochemical process through which nitrogen is converted into many forms, consecutively passing from the atmosphere to the soil to organism and back into the atmosphere. The first step is called the nitrogen fixation process. Here, atmospheric nitrogen, which is primarily available in an inert form, is converted into a usable form known as ammonia. During the process of the nitrogen fixation, the inert form of nitrogen gas deposited into soils from the atmosphere and surface waters, mainly through precipitation. The next step is nitrification. In this process, the ammonia is converted into nitrate by the presence of bacteria in the soil. The next step is assimilation, where plants take in the nitrogen compounds from the soil with the help of their roots, which are available in the form of ammonia, nitrite ions, nitrate ions, or ammonium ions, and are used in the formation of the plant and animal proteins. This way, it enters the food web when the primary consumer eats the plants. The next step is ammonification. When plants or animals die, the nitrogen present in the organic matter is released back into the soil. The decomposers, namely bacteria or fungi present in the soil, convert the organic matter back into ammonium. This process of decomposition produces ammonia, which is further used in other biological processes. The final step is called denitrification. Denitrification is the process in which the nitrogen compounds make their way back into the atmosphere by converting nitrate into gaseous nitrogen. This process of the nitrogen cycle is the final stage and occurs in the absence of oxygen. Nitrate contamination occurs in the surface water and groundwater, leaching into the soil and from there into the water supply from various sources. Irrigation water containing fertilizers is a common culprit, as are septic system, wastewater treatment plants, dairies, and natural conditions. Although a necessary nutrient for plants, high nitrate levels in people can harm the respiratory and reproductive system, kidney, spleen, and thyroid in children and in adults. It is particularly harmful to infants. Nitrate is expensive to remove from drinking water supplies, especially in public and private systems that rely on untreated groundwater and do not have the necessary water treatment infrastructure. A lake or water body is usually classified as being in one of three possible classes: oligotrophic, mesotrophic, or eutrophic. Oligotrophic lakes are most common in cold, sparsely developed regions that are underlain by crystalline igneous or granitic bedrock. Due to their low algal production, these lakes consequently have very clear waters with high drinking water quality. Mesotrophic lakes are lakes with an intermediate level of productivity. These lakes are commonly clear waters and lakes and ponds with beds of submerged aquatic plants and medium levels of nutrients. A eutrophic water body, commonly a lake or pond, has a high biological productivity. Due to excess nutrients, especially nitrogen and phosphorus, these water bodies are able to support an abundance of aquatic plants. Usually the water will be dominated by either aquatic plants or algae. When aquatic plants dominate, the water tends to be clear. When the algae dominate, the water tends to be darker. The algae engage in photosynthesis, which supplies oxygen to the fish and other creatures in the water which inhabit these waters. Occasionally, an excessive algal bloom will occur and can ultimately result in fish death due to respiration by algae and bottom-living bacteria. The process of eutrophication can occur naturally and by human impact on the environment. Eutrophication is a big word that describes a big problem in the nation's estuaries. Harmful algal blooms, dead zones, and fish kills are the results of a process called eutrophication, which occurs when the environment becomes enriched with nutrients, increasing the amount of plant and algae growth to estuaries and coastal waters. 65% of the estuaries and coastal waters in the contiguous U.S. that have been studied by researchers are moderately to severely degraded by excess nutrient inputs. Excessive nutrients lead to algal blooms and low oxygen waters that can kill fish and seagrass and reduce essential fish habitats. Many of these estuaries also support bivalve mollusk populations such as oysters, clams, and scallops, which naturally reduce nutrients through their filter feeding activities. Eutrophication sets off a chain reaction in the ecosystem, starting with an overabundance of algae and plants. The excess algae and plant matter eventually decompose, producing large amounts of carbon dioxide. This lowers the pH of the seawater, a process known as ocean acidification. Acidification slows the growth of fish and shellfish and can prevent shell formation in bivalve mollusks. This leads to a reduced catch for commercial and recreational fisheries, meaning smaller harvests and more expensive seafood. Nitrogen dioxide is one of a group of highly reactive gases known as oxides of nitrogen or nitrogen oxides, NOx. Other nitrogen oxides include nitrous acid and nitric acid. Nitrogen dioxide is used as the indicator for a larger group of nitrogen oxides. Nitrogen dioxide primarily gets in the air from burning of fuel. Nitrogen dioxide forms from emissions from cars, trucks, and buses, power plants, and off-road equipment. Nitrogen dioxide can interact with water, oxygen, and other chemicals in the atmosphere to form acid rain. Acid rain or acid deposition is a broad term that includes any form of precipitation with acidic components, such as sulfuric or nitric acid, that falls to the ground from the atmosphere in wet or dry forms. This can include rain, snow, fog, hail, or even dust that is acidic. Breathing air with high concentrations of nitrogen dioxide can irritate airways in the human respiratory system. Such exposures over short periods can aggravate respiratory diseases, particularly asthma, leading to respiratory symptoms such as coughing, wheezing, or difficulty breathing, then leading to hospital admissions and visits to the emergency room. In this section, we will take a look at ecosystems and how they play a major role in maintaining a sustainable balance for both humans and the world around us. Ecology is the study of relationships between living organisms, including humans, and their physical environment. It seeks to understand the vital connections between plants and animals and the world around them. Ecology also provides information about the benefits of ecosystems and how we can use Earth's resources in ways that leave the environment healthy for future generations. The study of ecology is important in ensuring people understand the impact of their actions on the life of the planet as well as on each other. Ecology allows us to understand the effects our actions have on the environment. With this information, it helps guide conservation efforts by first showing the primary means by which the problems we experience within our environment begin, and by following this identification process, it shows us where our efforts would have the biggest effect. Ecology also shows individuals the extent of the damage we cause to the environment and provides predictive models on how bad the damage can get. These indicators instill a sense of urgency among the population, pushing people to actively take part in conservation efforts and ensure the longevity of the planet. Ecology equally allows us to see the purpose of each organism in the web of connectivity that makes up the ecosystem. With this knowledge, we are able to ascertain which resources are essential for the survival of the different organisms. This is very fundamental when it comes to assessing the needs of human beings who have the biggest effect on the ecosystem. Energy conservation and ecology is connected in that it aids in understanding the demands different energy sources have on the environment. Consequently, it is good for decision making in terms of deciding resources for use as well as how to efficiently convert them into energy. Without proper understanding of energy facts through ecology, humans can be wasteful in their use of allotted resources, such as indiscriminate burning of fuels or the excessive cutting down of trees. Staying informed about the ecological cost allows people to be more frugal with their energy demands and adopt practices that promote conservation, such as switching off lights during the day and investing in renewable energy. With all the information and research obtained from ecology, it ultimately promotes eco-friendliness. It makes people aware of their environment and encourages the adoption of a lifestyle that protects the ecology of life owing to the understanding they have about it. This means that in the long term, people tend to live less selfishly and make strides towards protecting the interests of all living things with the realization that survival and quality of life depends on environmental sustainability. Here it fosters a harmonious lifestyle and assures longevity for all organisms. A great number of diseases are spread by vectors. The study of ecology offers the world novel ways of understanding how pests and vectors have therefore behave, thereby equipping humans with knowledge and techniques on how to manage pests and diseases. For example, malaria is one such leading killer disease that is spread by mosquitoes. In a bid to control malaria, humans first need to understand how the insect interacts with its environment in terms of competition, sex, and breeding preferences. The same applies to other diseases and pests. By understanding the life cycles and preferred methods of propagation of different organisms in the ecosystem, it has created impressive ways to, to control the measures and help kill them off. The term biodiversity refers to the variety of life on Earth at all its levels, from genes to ecosystems, and can encompass the evolutionary, ecological, and cultural processes that sustain life. Biodiversity includes not only species we consider rare, threatened, or endangered, but also every living thing, from humans to organisms we know little about, such as microbes, fungi, and invertebrates. Biodiversity is important to most aspects of our lives. We value biodiversity for many reasons, some utilitarian, some intrinsic. This means we value biodiversity both for what it provides to humans and for the value it has in its own right. Utilitarian values include the many basic needs humans obtain from biodiversity, such as food, fuel, shelter, and medicine. Further, ecosystems provide crucial services such as pollination, seed dispersal, climate regulation, water purification, nutrient cycling, and control of agricultural pests. Biodiversity also holds value for potential benefits not yet recognized, such as new medicines and other possible unknown services. Biodiversity has a cultural value to humans as well, for spiritual or religious reasons, for instance. The intrinsic value of biodiversity refers to its inherent worth, which is independent of its value to anyone or anything else. This is more of a philosophical concept which can be thought of as an inalienable right to exist. Finally, the value of biodiversity can also be understood through the lens of the relationships we have, form, and strive for with each other and the rest of nature. Ecological sustainability is the functioning of Earth systems working together across all ecosystems to regulate the planet. This includes climate systems, air, water, land, soil, biodiversity, and ecosystem services such as pollination and photosynthesis. A factor of ecological sustainability depends on the capability of ecosystems to regenerate utilized resources and repair themselves after disturbances or natural disasters. To reach ecological sustainability, the production of goods and services must not ruin ecosystems past their ability to function and recuperate. Water, air, land, biodiversity, and ecosystem services are all central to ecological sustainability. To reach sustainability, systems should be free of pollutants, protected from erosion, have a controlled climate, and maintain healthy levels of nutrients, salinity, and particulate matter. Maintaining ecological sustainability is important for the function of systems of the planet. Humans reap countless benefits from the sustainability of Earth, many of which we could not live without. Clean water, an essential human need, is greatly dependent on nutrient cycling, protection from pollutants, mitigations of drought, etc. All of these factors that breed clean and usable water can be easily disturbed if an ecosystem is not functioning properly, especially for those who rely on well water. Ecological sustainability also protects the planet from the overuse of resources. Resources like wood, water, and land area for human consumption must be monitored and tracked over time to ensure that humans do not dwindle resources past recovery. The Millennium Ecosystem Assessment was called for by the United Nations in 2000. Initiated in 2001, the objective of the Millennium Ecosystem Assessment was to assess the consequences of ecosystem change for human well-being and the scientific basis for action needed to enhance the conservation and sustainable use of those systems and their contribution to the human well-being. The Millennium Ecosystem Assessment has involved the work of more than 1,360 experts worldwide. Their findings, contained in 5 technical volumes and 6 synthesis reports, provides a state-of-the-art scientific appraisal of the condition and trends in the world's ecosystems and the services they provide, such as clean water, food, forest product, flood control, and natural resources, and the options to restore, conserve, or enhance the sustainable use of the ecosystems. Ecosystem services are the direct and indirect contributions ecosystems provide for human well-being and quality of life. This can be in a practical sense, providing food and water and regulating the climate, as well as cultural aspects such as reducing stress and anxiety. In fact, the vast number of services provided by ecosystems can be categorized into more manageable groups of provisional, regulating, cultural, and the slightly more ambiguous supporting services. These services provided by ecosystems lead to benefits received by humans in the form of security, goods and materials, health, and well-being. This slide shows the major divisions of the ecosystem services that are as follows. Provisioning. These are tangible goods that people can harvest from the environment, such as food, wood and fiber, water and fuel. Regulating. These are regulating services that occur in the ecosystem that lead to benefits such as climate regulation, flood management, and water filtration. Cultural. These include ways in which nature impacts people's health and well-being through recreational and education benefits, as well as improving mental health and building spiritual connections. Supporting. Ecosystems could not function without supporting services such as the nutrient cycle, soil formation, and habitat provision for biodiversity, forming the basis for the other three types of services. In simple terms, the precautionary principle conveys a common sense based advice to err on the side of caution. The principle intends to prevent harm to humans, environment, and ecosystems at large. The precautionary principle is a notion which supports taking protective action before there is complete scientific proof of a risk. That is, action should not be delayed simply because full scientific information is lacking. The precautionary principle or precautionary approach has been incorporated into several international environmental agreements, and some claim that it is now recognized as a general principle of international environmental law. Environmental law regularly operates in areas complicated by high levels of scientific uncertainty. In the case of many activities that entail some change to the environment, it is impossible to determine precisely what effects the activity will have on the quality of the environment or on human health. Often available scientific evidence provides us cause for concern but does not give conclusive information. In such scenarios, risk assessment compels us to strike a balance between the need to protect human health and environment on one hand and the foregone advantages of strict restrictions that may turn out to be unwarranted. Urban ecosystems apply the ecosystem approach to urban areas. Urban ecosystems are dynamic ecosystems that have similar interactions and behaviors to natural ecosystems. Unlike natural ecosystems, however, urban ecosystems are a hybrid of natural and man-made elements whose interactions are affected not only by the natural environment, but also culture, personal behavior, politics, economics, and social organization. Urban areas act as population centers, providing goods and services not only for its population, but also for populations worldwide. Urban ecosystems can no longer be considered as a separate entity to the environment as they have a direct and indirect impacts on the immediate and wider environments. Many of the environmental problems faced today, such as global warming, water and air pollution, and inadequate access to safe drinking water, can be traced back to cities and lifestyle choices. With urban population levels expected to reach 60% in the next 30 years and the majority of urbanization to occur in developing countries, urban environmental management is increasingly important. Urban areas cannot exist in isolation. They require inputs from and waste assimilation functions of other ecosystems. Ecological footprint analysis has shown that many cities require a productive land and sea area several times the city's size in order to support the population. Multidisciplinary in nature, urban ecosystem management requires a composite of social, environmental, economic, and decision-making tools and institutions that are flexible and can adapt quickly to changes in one or more systems. The urban ecosystem approach encourages the alignment of cities to that of natural ecosystems where resources, processes, and products are used more efficiently, creating less waste, requiring less input, and viewing byproducts as resources. Habitat loss refers to the reduction in the amount of space where a particular species or a group of species can survive and reproduce. Habitat loss is a consequence of human activities such as agriculture, urbanization, deforestation, resource extraction, alteration of the seafloor due to overfishing, or the release of pollutants. Habitat loss can also occur due to environmental changes such as volcanic eruptions or tsunamis or changes in climate or sea level, which today are largely the result of human activities. Habitat loss could decrease biodiversity and alter species ranges and interactions. Humans have altered Earth's land for thousands of years, but industrialization and population growth over the last 300 years, and especially over the last 70 years, has led to a great expansion in our land use and disturbance of habitats worldwide. Habitat restoration is the purposeful rehabilitation of an area to recreate a functioning ecosystem. Successful habitat restoration requires understanding species life cycles and interactions and the food, water, nutrients, space, and shelter that is necessary to sustain species populations. When habitats cannot be restored to their original size or condition, land can be set aside that connects open spaces and habitats called wildlife corridors that allow species to survive in and around areas occupied by humans. For example, marshes are an important resting spot for migratory birds, bridges allow animals to cross highways, and protected creek habitats create space for plants and animals even within developed areas. An invasive species could be any kind of living organism, an amphibian, plant, insect, fish, fungus, bacteria, or even an organism's eggs or seeds that is not native to an ecosystem and can cause harm. They can harm the environment, the economy, or even human health. Species that grow and reproduce quickly and spread aggressively with potential to cause harm are often given the label invasive. An invasive species does not have to come from another country. For example, lake trout are native to the Great Lakes but are considered to be an invasive species in Yellowstone Lake in Wyoming because they compete with the native cutthroat trout for habitat. Invasive species are primarily spread by human activities, often unintentionally. People and the goods we use travel around the world very quickly, and they often carry uninvited species with them. Ships can carry aquatic organisms in their ballast water, while smaller boats can carry them on their propellers. Insects can get into wood, shipping pallets, and crates that are shipped around the world. Some ornamental plants can escape into the wild and become invasive, and some invasive species are intentionally or accidentally released as pets. For example, Burmese pythons are becoming a big problem in the Everglades in Florida. The Anthropocene epoch is an unofficial unit of geologic time. It is used to describe the most recent period in Earth's history when human activity started to have a significant impact on the planet's climate and ecosystems. The term Anthropocene was coined to take into account the impact of the accelerated accumulation of greenhouse gases on the climate and biodiversity, and also the irreversible damage caused by the overconsumption of natural resources. But do we need to turn this into a new geological epoch? While the debate continues among scientists, solutions have yet to be found. This slide shows a path that can be taken to help slow down the effects of humans on the environment. While having all of these would take time, money, and a fundamental change in philosophy, they are being carried out incrementally around the world. When analyzing the reasons that have caused the appearance of this new geological age, we can speak of two main causes: the model of energy production and the resource consumption model. The energy produced from coal, oil, and natural gas emits large amounts of greenhouse gases, the main causes of global warming. For its part, the growing population needs a greater use of natural resources that nowadays surpasses the capacity of Earth to regenerate them. These human actions cause, among other consequences, changes in the water cycle, imbalances and destructions in the marine and terrestrial ecosystems, the increase of extreme meteorological phenomena, the acidification of the oceans, or the disappearance of forests. It is impossible to stop the devastating impact we are having on the planet. Although there are certain irreversible consequences, we can still mitigate much of the damage caused to the environment. It is necessary to tackle the problem at its root, decarbonizing the economy and relying in renewable and non-polluting energy sources such as the sun, the water, and the wind. Also, making a responsible and equal use of natural resources will help achieve a more sustainable system that can prevent the Anthropocene from becoming the last era of our planet.